Hi, my name is Hong Park, and I'm going to talk about GSSMD, a new standardized effect size measure which can improve robustness and interpretability in biological applications. This talk is organized as follows. I will introduce the motivation of our work and definition of overlap statistics and GSSMD. Some of the simulation results and real biological applications will be introduced, and I will conclude this talk with some of remarks. Let's assume that we have two probability densities, P1x and P2x. Assume that we want to solve a binary classification problem between these two distributions. Now I will call the P1x as class 0 and P2x as class 1. Then the risk of misclassification of a classifier becomes this equation. The total risk of misclassification is given as weighted sum of individual misclassification risk, as shown in this expression. If we assume the prior probability of class 0 or class 1 as 1/2, then the total risk becomes this expression. Assume that we have an optimal classifier with threshold epsilon 0. Since the classifier is optimal, the error of the classifier, or total risk of misclassification, is minimum. This quantity, reported as P minimum, is in fact correlated with the overlap between two distributions. If you call overlap as delta and assume prior probability as 1/2, then P minimum becomes delta over 2. In general, overlap between two distributions is given as minimum density between two distributions, as shown in this figure. Once we have delta, we could define GSMD as 1 minus delta to realize this quantity as differential measure, as shown in here. The sign operator is considered to provide direction of the overlap. If you have two normal distributions, you can have nice analytical equation that can provide exact value of delta. However, in other distribution families, we don't have nice equations for delta, so we need to estimate delta hat. Let me summarize two slides in one sentence. The total error of misclassification risk PE is defined by weighted sum of individual misclassification risk PM and PF, so delta is proportional to PE. In other words, this implies that estimated overlap between arbitrary distributions is a statistical metric which can provide an estimate of misclassification risk. Therefore, one wants to minimize this risk in their application. One needs to minimize delta or maximize GSSMD if they can minimize or maximize it. We show that overlap between two distributions can be used to get the optimal threshold of binary classifier. However, except normal distributions, we don't have an analytical equation to calculate this quantity. In addition, in real-world applications, we don't know the underlying distribution we work with. Therefore, we need to estimate delta hat to get the optimal threshold of our classifier. For this purpose, we developed a novel package called OverL tools, and it provides various overlap estimation methods. Here we apply OverL tools to estimate overlap between two normal distributions. Remember that for normal distributions, we have theoretical equation for delta. We ask which overlap estimation methods works best for the estimation of this quantity. Left-hand side figure shows the overlap estimation of each method when the mean difference of two normal distributions are varying -5 to 5. The red dots from triangle represent theoretical values. It seems that all methods work well except pink dots, which based on the k-nearest neighbor, and blue dots, which based on kernel density estimation. To objectively assess performance of individual overlap estimation methods, now we perform n equals 1,000 trials for single mean difference. As you can see in the right-hand side figure, histogram-based methods show the most accurate estimate, except the direct distribution fitting case. Since direct distribution fitting case requires understanding of underlying distribution, it seems that histogram-based method is adequate choice of estimation method. Here we used adaptive bin size selection method, which based on 1 plus log 2 of sample number. The overlap tools is available at the URL below. We see that histogram with adaptive bin size works well for estimation of delta. However, it could be too discretized when sample number is small. Therefore, we need to characterize finite sample behavior of these methods to fully utilize this method for the purpose. Here we use two samples from the same normal distributions. In other words, expected GSSMD is equal to 0. We performed 10,000 times of independent trials and used 3 to 10 to 6 number of samples to estimate upper bound and lower bound of GSSMD. For n larger than 100, the mean difference between estimated GSSMD and expected GSSMD was about 0.1. For n equal to 10 case, mean difference between estimated GSSMD and expected GSSMD was about 0.25. From this experiment, we conclude that over 100 number of samples, we can apply histogram-based method, although it's best if we have over 1,000 samples. We can apply this method when we have samples between 10 to 100, though the accuracy of estimation drops a little more. It's not recommended to use this method less than 10 samples, since they become too discretized. These small sample regimes, we can use direct distribution fitting or ECDF-based method instead of histogram-based method. For more discussion about effect of distribution type, sample number on overlap estimation, please see our manuscript and supplementary materials. Since we characterize overlap statistics delta, or differential statistics GSSMD, we could apply this measure to some of interesting applications. The first example is hit selection in RNA interference experiment. This dataset have two plates of RNA interference experiments, and each plate have positive and negative controls as illustrated blue dots and red dots on the figure. To objectively compare GSSMD-based criteria and conventional criteria called SSMD, we trained logistic regression classifier with samples from one plate and test the classifier with another plate. The optimal decision boundary of the classifier showed 96% of accuracy, and the type of error was 0.018. We asked whether GSSMD or SSMD-based criteria provide closed hit selection criteria compared to this optimal decision boundary. As you can see in the figure, GSSMD and SSMD provided a reasonably close decision boundary compared to the optimal classifier. GSSMD-based decision boundary showed narrower upper and lower bound compared to SSMD-based criteria. In addition, GSSMD-based criteria provided intuitive meaning. The threshold point is a 95.3% non-overlapping point between positive and negative control samples. But suitable SSMD criteria, which is -3, does not give any quantitative meaning, and it is hard to decide which criteria is proper for this case, since many readers also propose -5 as recommended criteria as well. We can also apply GSSMD for zero expression analysis. Due to the time limitation, I will briefly mention these results. Here we use GSSMD-based DZ selection technique based on permutation test. We compared the selected DZ with conventional DZ selection methods such as t-test and lemma. As you can see in these Venn diagram, they are well matched to each other. It's also possible applying GSSMD for multivariate case as well. To show this, we performed gene set activity analysis and compare with conventional methods such as single sample GSEA, GSVA, and plates. Here we use the first PC as kernel function, and thus the active gene set discovered by OVL tools are similar to those discovered by PlateG which utilized SBD. Overall, the results of 4 methods are well matched each other, as shown in the Venn diagram analysis in this figure. In this talk, I discussed about 3 things. First, we show that the distribution overlap between 2 PDFs can be used to selection of optimal decision boundary of a binary classifier. Second, we show that a new R package, OVL tools, can provide handy functions to estimate distribution overlap with various methods. Third, we show that we can apply OVL tools for various application areas, including but not limited to hit selection in bioassay, differential gene expression, and differential gene state activity analysis. The R package is available at the author's GitHub page, and we expect that many interesting applications can be tackled by creative usage of this tool. Thank you for your attention.